Our second speaker of the day today is Nikita Nekrasov from Simon Center for Geometry and Physics in Stony Brook, USA. So as we just learned, you cannot see Niagara Falls from there, but it's pretty much nothing you can see from there.
Right.
But okay, anyway, so today Nikita will talk about characters of field theories. So please, Nikita, the word is yours.
So, well, thank you very much for inviting me. I wish it were offline, but what can we do? So, I'm going to talk about the characters of field theories. That's a topic which confuses me a lot. So, many times I visited Brazil and I spoke about the instanton partition functions. So these are the complicated at first, but mathematically easier objects to define. And whenever I spoke about them, I would say that some kind of partition function. So this is a supersymmetric partition function of, let's say, n equals 2. T equals 4 gauge theory. It has, I would always write it as a product of something perturbative, and then the instanton contribution, and usually I speak about this part. Because it is it's sort of easier to define. So this is the sum over instanton charges, some fugacity for the instanton number, and then the integral over the modular space of instantons of something well, explicit, let me put it this way. And so these are finite dimensional spaces. So even though we came to this problem from quantum field theory, these are finite dimensional integrals. So this is something mathematicians can discuss. But the full partition function contains also this prefactor, which I usually don't have time to talk about. So this is what I want to talk about today. So morally speaking, this is the contribution of the true fields of gluons, gluinos, adjoint Higgs, etc. And there is no topology. This is just Feynman diagrams, and the beauty of supersymmetry is that these are only one loop diagrams. So in principle, it should be straightforward to calculate this all. But the subtlety is that we're not doing these calculations in conventional quantum field theory. This is the theory which is subject to some deformations having to do with the space-time symmetries. And so I want to, so the conventional Feynman diagrams are not going to be applicable. We need to modify them a little bit. So that's what I want to discuss today. But before we go here, let me just start with something more standard, and that's the topic of characters which you find in representation theory or in quantum mechanics. So this is another name for representation theory. And in a sense, you see, the quantum field theory perturbative calculations you can always reduce them to some kind of quantum mechanical computations by going to the first quantized picture. And so this is, so in some sense, quantum field theory is an exponential of quantum mechanics. So this is, please don't take this literally, but this is a kind of symbolic statement. So the computation of quantum field theory can be reduced to a bunch of quantum mechanics computations. So every time we look at the Feynman diagram, every propagator is some calculation of quantum mechanics suitably dressed and then superimposed over all vertices of the Feynman diagram. So we'll start with the quantum mechanical case. And so what do we have there? Well, we have some, let's say, Hilbert space. This is the space of states. And we have some symmetry group acting there. So these are in the conventional quantum mechanics, these should be unitary transformations. Actually, sometimes you can extend them to contain also anti-unitary transformations when there is time reflection. So that's why I put unitary in brackets. It's maybe too strong a restriction. And the quantity which we might be interested in computing is a partition function, twisted partition function, which is a function of an element of this group, the symmetry group, and well, the inverse temperature or Euclidean time. And so what this quantity is, it is simply the trace over my Hilbert space of the realization in this Hilbert space of the symmetry group G. And usually we put the Euclidean time evolution, the Hamiltonian. Right. So in other words, this is the partition function. You can think of this as a thermodynamic partition function of some quantum statistical mechanical system based on this quantum mechanics with chemical potentials associated with the symmetries. So if I write G as exponential of some, let's say, Lie algebra element phi, so these are generators of G, and these are parameters, then this guy is just exponential of phi a, the current, so the charge. This is the charge corresponding to the generator of G. So it's an operator in my Hilbert space. And so these parameters are simply the chemical potentials. So if this charge, for example, if one of these charges you associate with electric charge, then the chemical potential will be known as the electric potential. And but there could be other symmetries. So the question is, how do you compute this quantity? And in the path integral formulation, if this quantum mechanical system is obtained by quantizing some phase space, in symplectic form and with the Hamiltonian. So this is the classical phase space. The symplectic form. This is the function, so it's a classical Hamiltonian. Then the partition function is given by the path integral. So it's a path integral over the maps of a circle into the phase space. With some measure, symplectic measure. So I can write my symplectic form locally in canonical form with some double coordinates. Then, so we would write this as integral of p dq minus h. And then the group element G would be represented by, well, there are two ways of representing the group element. Either we introduce the twisted maps. So these are actually not the maps of a circle, but rather the maps of an interval, such that the value, so the interval of length beta, let's say, so the twisting means that the endpoints of the image of the map are related by the action of the group element in phase space. So we assume that this symmetry actually, so okay, sorry, I forgot to mention. So I'm assuming that the symmetry acts now on the phase space and preserves the symplectic form. So it acts in the Hamiltonian fashion. Well, okay, to act in the Hamiltonian fashion is something which Lie groups do. You can actually require that it acts in a way which preserves the symplectic form, so that way it can be applied to discrete groups as well. So there are two kind of important cases to consider. So for discrete groups, this is the so this definition is good. Let's say for finite or for discrete groups, but it is not very convenient for Lie groups, because for Lie groups we expect this quantity to be, so if G is a Lie group, the partition function is expected to admit analytic continuation to beta, which is complex, and the group element, which is actually it belongs to the complexification of the group. So let me just give you an example, and we'll go back to this classical picture. So if I take the group to be SU2, and the Hilbert space, just as a toy example, it's a space of states of a spin J, and J is a half integer. Let's say my Hamiltonian is 0, and the group element is just some diagonal matrix. Then, well, you can compute. Oops, using elementary tools that this is equal to the ratio of the sine j plus 1/2 alpha. And that clearly makes sense for alpha complex. Well, it has some singularities, has some poles when alpha is 2 pi times an integer, but otherwise it's well, it's a meromorphic function on the complex plane. And so it would be nice to have a definition of this character, which allows for the complex values of the group element. And so this is not good. So this twisted loops definition is not good because the complex group action doesn't preserve the symplectic form. So in this example, the phase space is actually just a two-sphere. The symplectic form is the well, just the area form on the two-sphere, which in spherical coordinates you can write, for example, as d cosine theta d phi. So this group element shifts phi by alpha, and if alpha is real, well, that's obviously a symmetry. But if alpha is complex, then the sphere is not preserved. So it's you need to have a so what happens is that this phase space sits inside some bigger space, which is a kind of a complexification. So this is a true sphere, and so this is my phase space, and it actually sits inside complex space, which is a real manifold, is a cotangent bundle to the two sphere. And so if I'm applying an element of the complexification of the so G is the group SU2, and the complexification of SU2, as you can guess, is SL2C. So the two sphere I can view as sitting inside the three-dimensional Euclidean space, and described by the usual quadratic equation. Let's say 1. So the complexification of the sphere sits inside the three-dimensional complex vector space, and it is given by the same equation, but now with x, y, and z complex. So now if I apply linear transformation x, y, and z with complex coefficients given by the matrix from SL to C, then of course I will remain inside this complex space, but will not remain on the real phase space. So something has to be modified about the definition of path integral, which would admit such complexified parameters. And so what one can do, one can generalize this definition in such a way that it will admit the complexification without any sweat. So this is how to do it. We'll be integrating now over strictly periodic maps, but instead we will introduce the background gauge field. So I will introduce the parameters valued in the Lie algebra, multiply them by some function. So mu's are the moment maps components, the components of the moment map. So these are the Hamiltonians on P, which generate the group action. So the Poisson brackets, for example, should obey the commutation relations of the Lie algebra of the group G. There are various, I mean, almost everything I say is not literally true because there are subtleties at every step. For example, this commutation relation might be spoiled by additions of constants, by central extensions and things like that. But let me assume for simplicity that this doesn't happen. Then these A's are external parameters. And even though it looks like I've introduced now the functional parameters because they could be arbitrary functions of time, we will check immediately that actually this quality, this integral only depends on these parameters up to a gauge transformation. So for any g of t, so for any periodic function of time valued in a group. So this is because applying such a transformation, I can undo this by applying simultaneously the field redefinition when I replace my loop by the loop on which I applied the symmetry, the time-dependent symmetry transformation. So this is so in this way, this path integral only depends on the conjugacy class of this gauge field. So this is the so it's an external gauge field. It's not, we don't gauge, we don't integrate over A, we just keep this as a parameter. And the partition function only depends on the conjugacy class, that is to say, it's the conjugacy class of the group element, which is a path ordered exponential of A. Up to the similarity transformation. Are there any questions so far?
I have a short question. So what was before chemical potentials, right, for element G? These are now these A's, right, encoded A's.
Well, so the chemical potentials are kind of a zero modes of those A's. So I should compute this path ordered exponential of A, and then if you like, I can write it as an ordinary exponential of some Lie algebra element. So this phi's, if you like, I can also write this in the more expanded form. So these phi's are, roughly speaking, so these are the integrals of A plus some corrections, which I don't know, maybe some.
Okay, thanks.
So they're complicated functions, those guys. But you can make them, if not a little less complicated, by going to the gauge, where, so there is a gauge where A is essentially constant in time, and then phi will be just the zero mode, just the constant times beta, essentially. All right. So okay. So this is. It looks like we've gotten a complicated expression.
Sorry, Nikita. There's one more question. Maybe.
Yes, please.
Nikita, for the gauge field, what's the measure you adopt?
This is the external parameter. We don't integrate
external. You're not going to integrate it.
No, this is.
Yeah.
You see, this is what my. So this external parameter becomes this G. So
Okay.
it's the argument of my function.
Yeah, yeah.
I'm not integrating it.
But tomorrow, in the next lectures, you're not going to integrate over G. You have a full.
I'm integrating over P. So I'm integrating over P and Q. And I imagine that the measure of integration, even though this is very naive, but I imagine that this measure is just the product over each point on the circle of a symplectic measure,
Okay.
so the Liouville measure.
So there's no.
It is naive because
R measure, for example.
But for the gauge fields, yes, you could. Okay, so good question. So if I know this character, then by averaging with the Hauer measure, if it exists, I will get the dimension of the space of invariance.
Sure.
So here you use the Hauer measure. That's just one use of such character, because in general, my Hilbert space will split as a sum of representations of my group, and to isolate a specific representation, you can do that by integrating this way. So if you just average over the group, you'll get the space of singlets, the dimension of the space of singlets. If you insert some character in this integral, you will get the space of states which transform as a specific irreducible representation of the group. But what I want to
There's one more question. I'm sorry. Please, Agostino, please.
Oh, yes. Can you hear me? Yeah.
Yes, I can hear you.
No, two questions, in fact, related. Why do you need the complexification of the group G? And second, the example you gave for SU2,
yes,
you took finite dimension of representation.
Yes.
And that's not unitary if it's a complex group, right?
So it's unitary for this compact group.
Yes.
But,
okay.
But as you can see with your naked eye, this character admits the analytic continuation to complex group. So it's just a fact of life that this function makes sense. So it means that the original definition should admit an extension to complex group elements, which obviously don't act in a unitary way, but it just says that unitarity of representation, it's not needed for the character to be defined.
So essentially you are taking the Weyl character formula and complexifying the parameters that appear there.
Well, I'm just taking the character formula, which you can compute without, if you know the elementary school methods of summing up a geometric series. So you don't need to know Hermann Weyl at this point, and you can just observe that this function makes perfect sense for complex values of alpha. Right? So you can, for example, you can make alpha to be imaginary, and well, it makes sense. So it is something, but what does it compute? You can ask, what does it compute? Okay.
Now, but the first question: why do you need G to be complex?
I don't need. It's a how to say this? Well,
I think it's related to the question what it computes, right?
Okay, so suppose you want to compute this integral over the real line. Well, you can compute it by going to some, making change of variables, finding the right, or maybe you can do it numerically. But you can also observe that this guy is a meromorphic form on the complex plane, and so you can do the residue calculation. So even though your question, the original question, only had to do with real values of x, maybe it was some probability distribution, I don't know. but it's beneficial to know that it admits analytic continuation to complex plane, because then you can deform the contour. Well, you can do many other things, but it's useful. So I don't need it, but it's useful.
No, I thought there was a physical. Okay, it's a mathematical. Okay, thank you.
But that's the point. So I'm saying that since it makes sense mathematically, maybe it should make sense physically as well. So what's the physics of that? Well, I'm asking, what does it mean? What's the left hand? How should I modify the left hand side so that the right hand side becomes this analytic continuation? And that's the answer. So now, once I have this parameters of the twist in the exponential, I can make them complex. In statistical mechanics, you do analytic continuation chemical potentials all the time. When we relate the quantum mechanics to statistical mechanics, we do this analytic continuation in time.
Okay.
We replace time by the imaginary time, and that becomes inverse temperature. So that's what we do. You can ask, why do you need complex time? Well, thermometer tells you. So it's the you might say it looks like a trick, but it's a useful trick first, and it might have some physical significance second. And black holes. I mean, if you want to talk about black holes, you do this analytic continuation all the time. Black holes are complicated and I would say a bit controversial, but quantum field theory on a fixed space-time is probably the better starting point to do this. Any other questions?
No, I think we.
Okay. Good. So this can be complexified. And once you can complexify something, then you can hope to gain the computational power, because you can do things like residue calculations. So this is what I was getting at. Another point where you can complexify, you can try to complexify this whole integral, meaning that, just as in this example, so modify this integral. So this original integral was over the real line, but then you can deform it and maybe close it over the singularity, and then compute by the residues. So maybe the same can be done for the path integral. So it turns out that for certain path integrals, yes, it is possible, and that's and so the integrals which compute the characters are actually the best cases where this works, and so this leads to the so-called fixed point formulas. Which you can understand sort of intuitively in the following way, that if you think about the original question, which was the computation of this trace in the semi-classical way, so it was like a sum over the, so this is, okay, so on the one hand, this is just the sum of diagonal matrix elements, right? And I'm skipping the Hamiltonian here, because that's the point which I'm going to make is about the symmetry. So if in some sense you could identify this with the action of group G on the phase space, so if you can sort of identify this with some points on phase space, more precisely, well, we don't identify the states in the Hilbert space. We associate not with points in phase space, but with Lagrangian submanifolds, actually. So there's a Lagrangian submanifolds. For example, if you think about the wave function is a function of x, so given x, in the phase space. So X corresponds to the whole set of momenta. And so this is a half-dimensional submanifold in the phase space on which is impacted convention. So that's Lagrangian submanifold. And so taking a diagonal matrix element of G, so how does G act? Well, G moves the Lagrangian submanifold. So for example, if my symmetry is some kind of rotation, well, it will rotate my Lagrangian submanifold, and the matrix element, well, intuitively should come from something like an intersection of the Lagrangian with its rotated image, and so these are essentially the fixed points of G action on the phase space. And so this is now Hamilton, which was mentioned. So that's the ideology, you might say, that the character should be given by the sum over the fixed points of G action on the phase space, and then each fixed point should give some local contribution. So some okay, there is a numerator and denominator, and so this is what I want to discuss. So this is some local contribution, which in the path integral I was writing before. Let me set now the temperature to 0. So let me just set Hamiltonian to 0 for a moment. So this local contribution is a contribution of a loop which is actually constant, and it maps to the point which is being fixed by the action of the group element G. So G on X is equal to X. So for example, in this example of the two-sphere, which I gave, the unitary group element so the diagonal matrix or diagonal some basis, it acts by rotating the sphere. It has two fixed points. So if I parameterize my sphere with the so this is the so there is I forgot what it's called, azimuthal angle and the polar angle, right? So so each point has the angle theta, so that's the theta, and there's the angle phi. So so phi is shifted by alpha, and so this point is fixed when phi doesn't make sense. So phi doesn't make sense when theta is equal to 0 or theta is equal to pi. So these are two fixed points. And so that formula, which you could get from elementary school now can be written in a more sophisticated way. So this is the contribution of the North Pole, and this is, including the minus sign, it's a contribution of the South Pole. So this you can get by looking at this integral and doing the approximating this integral near the constant loop by Gaussian integral, and just computing it as an infinite dimensional Gaussian integral. So that's an approximation, but the miracle is that it's an exact approximation. So that's going to be the full answer, and that's the elementary school calculation which confirms that. So this is exact answer, even though at first sight it looks like, well, the sphere is curved. The original integral we're computing was not Gaussian. So what's going on? Well, there is a trick to make this kind of more explicit, and that's the trick is to introduce supersymmetry, which would transform the coordinates in phase space to some fermions, and those fermions
There's a question, Nikita.
yes.
Me again, sorry. This 6-point image, you have it even if the group is non-compact, and you have an exact value also for SU3, SU4, and so on.
Of course.
But when you have a non-compact group, what happens? I mean, you have an infinite amount of fixed points, or?
Well, it depends on the space. It depends on the space on which you act. But the point is that okay. Remember, I mentioned that there is a gauge which you can choose for these external parameters. So one thing which you can do, you can always choose this them to correspond to the Cartan subalgebra of your symmetry group. Depending on which Cartan subalgebra you choose, for non-compact groups, you have different Cartan subalgebras. For example, for SL2R, you can have the subalgebra which corresponds to the compact subgroup SO2. So even though the group is non-compact, its maximal torus could be compact. And it depends on which space your group acts on. So if it acts on the one polar hyperboloid, for example, then there is a group which acts by rotation. It will have only one fixed point. So that's even though the group which acts here is non-compact, SO2R, the maximal torus which acts here is compact and has one isolated fixed point, and that gives you the correct character for the principal series representation. But there are other groups, so you can also choose a different subgroup, for example, R of the upper triangle matrices, and that will have no fixed points, so that the character will have to be understood as a generalized function. And maybe that's what I should speed up and talk about this, because that's
Thanks a lot.
Okay, so let me just finish with this line of thought that you can promote my action by adding something which looks non-dynamical, so it just the fermions will enter without derivatives, But the advantage is that you can now add some regulators with an arbitrary coefficient. I'm being schematic here. So with a very large coefficient, which will, on the one hand, it will not change the answer because this is the exact term. So this is like the total derivative in the path integration domain. But when t goes to infinity, the integral will be localized onto fixed points with arbitrary with precision. Okay, so now I want to go to the point of my main interest today is that how to generalize this to the infinite dimensional case. So now I want H to be the Hilbert space and because of lack of time, I will do it for the quantum field theory in the odd-dimensional space-time. In odd space-time, odd not in superset, but in just that in the usual sense, so that my space will be even dimensional. And what I want to compute the trace of the action on this Hilbert space of states of quantum field theory. And I want to insert the group element which belongs to the group of rotations. So it's a subgroup of the Lorentz group, of course. And I will also insert the Hamiltonian. So that's what I want to study. And of course, well, in general quantum field theory, this is a very complicated object because, well, that object knows everything about the spectrum of the theory, and not only the spectrum, but also its decomposition under its spin content. So it's probably hopeless to compute it in general quantum field theory, but if my quantum field theory is supersymmetric, then I can insert an additional symmetry element, the fermion parity, and so that object has chances of being computable if the symmetry group element preserves some supersymmetry. So what it means is that it has to be actually embedded. It could not be just a rotation because rotations act on spinors, and spinors are the generators of supersymmetry summation. So no rotation will preserve a spinor, but typically the extended supersymmetric theories, so n greater than 1, in addition to superpoint Carré symmetry, they have some global symmetries like R symmetry, or the symmetry which rotates the different superalgebras inside the extended superalgebra. And so together with the rotation combined with some of the internal symmetries can preserve this supersymmetry. So for example, if 2n equals to 4, so that means that we are in 5 dimensions. And capital N is, well, okay, so then the generators of supersymmetry they have two indices. So if you take minimal supersymmetry in 5 dimensions, from the 4-dimensional point of view, this is actually already an extended supersymmetry. And so alpha is 1, 2, I is 1, 2. This is 4D spinner. Sorry. This is, it's kind of a, well, it's an R-symmetry index. And so this is anti-chiral spinner of, let's say, chiral CS minus, and also R symmetry. So I could have G, which is in SU2, which embedded diagonally into the SU2 left cross SU2 right cross SU2 symmetry. So if this G is embedded diagonally into, for example, this product, then the linear combination of these spinors will be invariant. For any choice of G. And in addition, you can also have a U1 symmetry, which preserves. So you can also embed, have U1 in the other SU2, which will also preserve that supercharge. So so that means that you have some freedom for the choice of these twist parameters, which would be compatible with some amount of supersymmetry, and so that you might hope to be able to compute this quantity. So, and to be able to compute it means that by some deformation you can reduce this computation to the computation of free fields in free fields. So when you turn off all the interactions in your theory, and just like in this example, you can basically linearize your phase space around one of these fixed points and to the arbitrary good precision. And then the computation becomes exactly the computation like a Gaussian integral. So let me just give you a flavor of what these Gaussian integrals look like in a field theory case. And that will be the conclusion of my talk today. So, so using supersymmetry, one can deform the Lagrangian of the original quantum field theory to that of the free theory. So it becomes a bunch of well, scalars, maybe scalars, fermions, vectors, etc. And so we need to be able to compute this trace for each of these guys. So let me show you how you do this for the scalar fields. So if this is my theory, maybe it might have a mass term. And remember, we are in 2n plus 1 dimensions. So we have 2n spatial dimensions and we have time. And now I want to introduce these twisted boundary conditions that I have a rotation acting on spatial indices. So basically, in this first formulation, when we just look at the twisted loops, my path integral is over the space of fields which depend on x and time, such that phi of x at t plus beta is equal to phi of g dot x ft. So this is the twisted boundary condition. So this is what I want to compute. I want to compute. Now my time is periodic with period beta, and Lagrangian is quadratic, but there is a twisted boundary condition. So that's the subtlety. So how do you compute that? Well, okay, I'm using the second quantization to say that the trace of the bosonic Hilbert space e to the minus beta h g is actually given by the so-called platistic exponent. So this is one particle Hilbert space. So this is something like you can get this. So the path integral which we were about to compute was given by the 1 over the square root of determinant of some operator like that with twisted boundary conditions. But then if you write the determinant as exponential of the trace of a logarithm after some dealing with the time variable, you will get to this form. So this is called platistic exponent. So this is something which you find all over and over again. So now the one particle Hilbert space well, it's essentially the space of functions of x of the space coordinates. So these are the wave functions, the spatial parts of the bosonic wave functions. And so I want to compute the action of the rotation group, and then there is a Hamiltonian also. The Hamiltonian is well, it's a square root of the t squared plus m squared. So it's a square root of m squared, minus a Laplacian. So that looks scary, but we have a basis of, so we can write this as a linear combination of momentum eigenstates. And so in that basis, the Hamiltonian acts simply by well, it just multiplies the wave function by e to the minus beta energy. So that part is easy, but now we have g. So g rotates the x variable and simultaneously rotates the momentum, if you like. So what I need to do, I need to compute the matrix element of the rotation between two momentum eigenstates. And so how does what is it? So the momentum eigenstate, it's the function e to the ipx. So if I apply the rotation, I will get e to the ip g dot x. Okay. And now if I want to compute the diagonal matrix element, well, I need to integrate over the space. Right, so and this integral is actually very easy. So it's a delta function of g inverse p minus p. And so and this is where the even dimensionality of space becomes important. That's because for generic g, So generic G can be block diagonalized with n blocks. So each block is the matrix of the form cosine theta, sine theta minus sine theta, sine theta. So this is I. And so G inverse dot P minus P, well, so I need to act. So the inverse matrix will have just the sign changed. So I need to, so I split my P also into the now components of, into the blocks of length 2. Also n blocks and components. Size 2. So this is, so delta of that is just the product over each of these blocks. Then I have delta function of cosine theta I pi plus minus 1 minus sine theta I pi minus. So this is what this block acts on. Times delta of sine theta I pi plus cosine theta minus 1 pi minus. Well, it's a little simple manipulation with these delta functions, which will tell you that it's essentially delta of 2n of P. So the only non-contribution comes from P, which is equal to 0. And then you divide by the product over 1. I think it should be 2i. You need the determinant of this matrix, so that's going to give you doubling of the angle. So this is the integral, and remember we had also the contribution of the energy. So even though the energy function is kind of a complicated function with relativistic dispersion law, because the integral is saturated by the contribution of zero momentum, it is just e to the minus beta m divided by this. So this is the single particle trace, and in order to get the contribution to the scalar contribution to the field theory partition function, we need to take the logistic exponent of that. So this is sum 1 to infinity 1 over n, and then this guy can be written in a more suggestive form this way. So this is 1 minus n theta product over. So remarkably, in odd space-time dimensions, this partition function actually has a limit when beta goes to 0. So you don't need the temperature to regularize this partition function, and it's essentially as you would expect from the well, here I didn't use supersymmetry at all because this was just a free field computation for a single boson, for a single scalar field. What happens when you so if you add now supermultiplet, what happens is that one of these factors gets canceled. So that you will get, so the boson in the numerator contributes 1, and then you will have the, let's say if you have a vector multiplet, you will have the gluinos, which will contribute minus the sum of I theta in the numerator, and then you will have vectors which will contribute plus theta, something like that. So they will precisely arrange themselves into a product which will cancel half of the numerator, and that's the perturbative part of the supersymmetric partition function, which you actually find in this instanton computations. So sorry for being a bit cryptic, but I hope I conveyed at least the spirit of some of these computations. Thank you very much.
Okay, thank you very much, Nikita. So let us open our microphones to thank Nikita for his lecture. And now we are in the discussion time. So